First of all, I think welcome everyone to like the new season of Aleks Seminar Talks. I think we already have a full lineup now, Sarah, of like 12 talks in a row. Website on the seminar page, it already has the schedule there, so you can see who is talking when. The standard time is this time 3 p.m., but I think there is at least one exception where it will be a later time because the speaker is from the US. Um, Yeah, so for this inaugural edition, we have Alex, who will be talking about our book. So yeah, I think I don't want to say much more about that. Just let Alex do the talking instead. So Alex, you can get started if you want.
Okay, thanks, John. A couple of weeks ago, Sarah and John had this idea that we give this talk after discovering maybe not everybody knows about this book, or maybe if they do know about this book, they might not know what all is in this book. So I thought I would give a bit of an overview of our new book, our new free book called Picturing Quantum Software. These slides are available online. I just stuck the link in the chat. It's also on the Discord, and there are links sort of throughout. So I guess the most important thing is how do you get this thing, right? If you go here to what is that, zxcalc.github.io /book, you get this page. There are two versions of the book. There's a PDF version and an HTML version. I guess I'll stick this link here as well. And also, if you are following along with these slides, if you click on any of the titles here, it will just jump to that chapter in the HTML version. So hopefully that people will find pretty convenient. So let me get started. So what is this book about? Well, this is a new textbook introducing core quantum software and compiling concepts, all using the language of ZX. So some of these things were originally invented in ZX calculus, but the vast majority of these things are mainstream quantum software concepts, which we're teaching sort of through the lens of ZX. And this makes a lot of things easier to understand and also easier to kind of push farther than things have been before. Okay, so let me just get stuck in. I'm going to go kind of chapter by chapter here, but then I'll dig down a little bit when I think there's particularly interesting or nice things to mention. Okay, so what do we mean by quantum software? And I guess this is kind of a question about what the scope of this book is. So quantum software is really just the code that runs on a quantum computer. So that could mean a circuit or a measurement pattern, something like that. And really the scope of this book is quantum software, basically everything else besides algorithms. Okay, so on the one hand, you have the algorithm, on the other hand, you have the hardware. And what this book is about is really everything that's in between. So getting from algorithm to hardware. I guess many people here are very familiar with the ZX calculus. This is a convenient graphical language for reasoning about quantum software. One of the reasons for that is that ZX diagrams, which are the syntax of ZX calculus, very easily express quantum circuits. So for instance, here's a universal family of circuits in ZX notation. And it is complete with circuit equality. Okay, so if I write a circuit out in ZX notation, then just using a few simple rules, I can transform that circuit into any other circuit which describes the same unitary. Not necessarily efficiently, but for certain fragments of circuits, this is efficient. So this has been used to great effect for the past 15 plus years for reasoning about qubit quantum computation. So many people have seen this little toy example before, so you can take a circuit like this and interpret it as a ZX diagram, and then applying these simple rules, you can simplify it to something that's much smaller. Okay, and this is possible to do at the gate level, but it's a bit more unwieldy. Okay, so that's kind of what I want to say about, by way of introduction. So where this book starts, where this material really kicks off, is chapter 2. So this book is pretty self-contained, and it starts with a intro to quantum theory and quantum computation, um, and it introduces this the way I like to teach it in my lectures using the SCUM acronym. So this is about a 50-page intro to quantum theory, hitting kind of the core, what I would call the von Neumann postulates, but in the book we call it the SCUM postulates. So describing states, compound systems as tensor product, unitaries, and measurements. Okay, so if you want to teach using this book, you can give a whole course just from this book. Though you might want to augment it with a bit of other stuff. Many of these things you would also find in Nielsen and Schwang. Something that you might not find in a typical textbook is as an intro to tensor networks and Penrose diagrams. So really how you can make sense of string diagrams as tensor contractions. Okay, so with that out of the way, we move on to kind of a chapter introducing the basics of ZX calculus. So people that are familiar with ZX, this will be very, very familiar territory. Really just giving the rules, also some intuition behind the rules, how these connect to other things in circuits and in computation, and a bunch of examples and exercises. Okay, so here's a fairly familiar example where we have quantum teleportation written as a ZX diagram, and you can see that through applying the rules, you can verify that the protocol works. Okay, so we have simple things like teleportation, magic state injection, some sort of circuit simplification things in this chapter. In chapter 4, this is really where the good stuff starts. Okay, so this is really where things that some of it was pre-existing, but also we started to figure out some new stuff for this book. And this was in working out the structure of the phase-free ZX calculus. So this is where all of the phases are set to 0. So we get ZX diagrams really just of Z and X dots with no phase angles. And these are quite closely related to CNOT circuits or parity circuits. Okay, and this is what a CNOT gate looks like. So in this chapter, we talk about CNOT circuits, which correspond to parity maps, which are maps which send lists of basis elements to lists of XORs of basis elements. Okay, so you may have done an exercise like this with a CNOT circuit before, where you label the intros with some variables, and then you just carry those variables through the circuit, and you can see some XORs on their outputs, right? So this is quite a useful way of thinking about what a CNOT circuit does. And using this fact, you can efficiently represent the action of a CNOT circuit and also synthesize or resynthesize CNOT circuits using Gaussian elimination. So the phase-free ZX calculus is also very simple. It's essentially what I would call two rules. So we have the spider fusion rule. You might want to say that this identity rule and the scalar rule are kind of part of the spider rules. And the most important thing is this strong complementarity rule. And then applying those two rules, you can actually get a complete graphical calculus for this fragment, so for the phase-free diagrams or for CNOT circuits. And the way that you can prove completeness is reducing things to this new normal form that we introduced, which is called the generalized parity form. So when in this generalized form, you notice that we've got some Z's on the inputs, some X's on the outputs. They're connected by some wires, and then we have some sort of extra nodes here. So these are quite useful for quantum error correction later. But when we're thinking about CNOT circuits, we can assume that these are 0. And when those are 0, we can just represent the action of this map by some Boolean matrix. And what this unitary does is it just maps a basis vector to this Boolean matrix times the basis vector. Okay, and if we zoom out a bit, this is kind of a first preview of the scalable notation. Okay, so the scalable notation turns single wires into registers of wires, like these bold wires. And the really interesting thing that it adds are these matrix arrows. So these things like this. Okay, so bits of scalable notation are kind of sprinkled throughout the book, especially when it makes things especially nice or easy to work with in a general way. So working over these registers. So for the rest of this chapter, we show how the phase-free rules correspond to lots of things from linear algebra over the two-element field. So here's kind of a nice intuition. So this strong complementarity rule is really something like variable substitution. Okay, so here you can think, here's a phase-free diagram that I'm kind of tracking the parities through. And when I apply strong complementarity here, it's really like taking this variable y1 and substituting it for its value, which is x1 plus x2. Okay, you can kind of see that that's what's happening when I'm applying the strong complementarity rule. Okay, and lots of things that you would do in linear algebra have this kind of flavor. So you can really think about graphical versions of doing Gaussian elimination, of changing the set of spanning vectors for a subspace. Computing, say, the ortho complement of a subspace. All of these things are quite relevant, and they have applications when thinking about CNOT circuits, also thinking about error correcting codes. Okay, so in chapter 5, and this was probably the thing that we put the most thought and energy into. So in a way, it's kind of the center point of the book, is about Clifford circuits and diagrams. Okay, so like I said, the ZX calculus is complete, so we can prove that any two circuits are equal using the ZX calculus. But the Clifford ZX calculus, well, it's also complete, but more usefully, it's efficiently complete. So what does that mean? If I have two Clifford ZX diagrams, so these are diagrams where I restrict the angles to multiples of pi by 2. If they're equal to each other, I can not only prove that they're equal to each other using the rules, I can do so in polynomial time. So in this fragment, we have a complete set of equations, which lets us do efficient synthesis of Clifford circuits, efficient equality checking, and efficient strong classical simulation. Okay, strong simulation means that we're actually computing arbitrary marginal probabilities. Okay, so that's at least as good as classical simulation, because once we know probabilities, we can sample from them. So these Clifford ZX diagrams are very closely related to Clifford circuits. So Clifford circuits are built from CNOT H and S, and then you can see that the unitary Clifford ZX diagrams are really just the things that I can decompose into this gate set. So using the Clifford ZX rules, we can efficiently reduce to normal forms. In this book, we quite often use one of two different normal forms. So some people might be familiar with this GSLC form. So this means graph states with local Cliffords. So this has been around for a while and goes back to the original completeness theorem of Bakens for the Clifford fragment. But what's also quite handy is this AP form. So this means affine plus phases. Okay, so this is the reason it's called this is you can think of this part of the diagram as describing some affine subspace, and this part as describing some phase polynomial, some phases I'm going to assign to vectors in that subspace. Each of these have their uses, and they come up many times in the book. So these normal forms are used for Clifford circuit synthesis or resynthesis. And something that's quite nice that we did here is give purely ZX proofs of efficient equality checking and the Gottesman-Nil theorem. So for classical simulability, you can really just give pure rewriting proofs of this. So you don't need any stabilizer theory to prove this. It's really just take my circuit, plug up the inputs and outputs, and just run some simplifier, and out pops a amplitude, and then you can use that for efficient classical simulation. So even though you don't need stabilizer theory for Gottesman nil, it is still quite interesting to look at stabilizer theory and how it relates to the Clifford-ZX calculus. So this chapter on stabilizer theory is really about kind of establishing a dictionary between the Clifford-ZX fragment and the kind of mainstream stabilizer literature, which is kind of the main language of quantum error correction. One of the ways we do this is via a ZX representation of multi-qubit Pauli measurements. We call these things Pauli projectors. You can see that it's written as a big box labeled by a Pauli, and then this thing, which is the measurement outcome or the choice of the plus one or minus one eigenspace, represents the measurement outcome as a spider. I guess these one of the first kind of main applications of these Pauli projections is we prove what I like to call the fundamental theorem of stabilizer theory. And this is, I think, a very familiar concept to anyone working in this, but I don't know if this terminology is so standard yet. But this is the idea: if I have k independent stabilizers, then the image of their projector is n minus k, right? So this is this idea that if once I fix a bunch of independent stabilizers, this fixes a subspace, and the size of that space is sort of chopped in half with each new independent stabilizer. In particular, if I fix n of these things, then that uniquely fixes a state. Okay, and this is really, in my mind, why stabilizer theory works, right? Because it really helps you uniquely pin down subspaces and states efficiently as well. Okay, and using this language, we can prove equivalence of tableau and ZX representations of stabilizer states and maps. Okay, so that first part of the book is all about the efficient stuff. So these are the things that we can really do exactly and efficiently, and up to and including the Clifford fragment of ZX calculus. In chapter 7, we start to go beyond that. So we talk about universal families of circuits. One of the first things we cover is efficient representations of CNOT plus phase circuits using phase polynomials or their graphical version, which are called phase gadgets. So here you can see we started to sprinkle in some Z phases into these CNOT circuits. These still have a very tractable, very manageable structure. We get some nice normal forms, which are quite like the phase-free normal forms, except now they're decorated with these phase gadgets. Which tell you something about the phase of basis states that get passed through. We talk about circuit optimization via phase holding. So here you can get situations where I have phase gates, which can be quite far from each other, but they can still cancel out because they act on the same parities. And you can see this is fusing these phase gadgets into each other. This is, I would say, one of the first and most useful ways to do circuit optimization for non-Clifford circuits is to look at this phase holding move. We also talk about various representations of universal families of circuits, including the sum over paths or Feynman sum, discrete Feynman integral representation. So some people might be familiar with this from Matthew Amy's work and his Feynman tool. So these are quite related to these kinds of diagrams, especially once we start sprinkling in some H gates in here, then we'll get some summations appearing. And also Pauli exponentials. So Pauli exponentials are a way of a very general family of multi-qubit phase gates. And finally, the place that this chapter culminates is with Hamiltonian simulation via trotterization. So these things, these chunks, are the Pauli exponentials. And we show how you can take some arbitrary Hamiltonian, which is being exponentiated like this, and you can pull out these Pauli exponentials kind of one at a time, incurring some error as you go. So this is a kind of standard elementary technique for writing a circuit which simulates, or at least approximates, the time evolution of some physical Hamiltonian. Cool. So that's the first half. Well, first half of the book. Yeah, I guess about the first half of the material as well. In the middle of the book is just a bunch of cheat sheets. Okay, so these are just lists of tables, of rules, and normal forms, and all this kind of stuff. So this is all in one place there. Right. I don't think there's much more to say about that. So in the second half, we start talking about some more advanced materials. So in the first 7 chapters, we built a bunch of tools for working with ZX diagrams. And in the last few chapters, we really apply those tools in various ways. And the first is in chapter 9, we talk about how a tool like PYSIX, for instance, does circuit optimization, and the kind of theoretical relationship between that and measurement-based quantum computing. Okay, so the way we kind of originally started doing circuit optimization with ZX calculus was in 2 phases. So the first was simplification. So this was taking some circuit and applying a simplifier to it, reducing it to some kind of normal form, or at least some minimal form, and then doing some circuit extraction. So this is taking this now minimal thing and trying to pull out gates sort of stepwise until we get a circuit. So unfortunately, this is hard. So this is number P hard in general, but it can be done in polynomial time with the presence of a graph theoretic property called generalized flow. So the reason that we where this concept of generalized flow comes from is measurement-based quantum computing, where you would look at measurement fragments, so these measurement patterns, and think about applying single qubit measurements and where I need to correct those measurements forward in time. And it turns out that this criterion, which is called generalized flow, which says, I have a kind of a efficient routine for finding these corrections, is also a useful, sufficient condition for being able to extract circuits. Okay, so in this MBQC chapter, we explain all of these things, and from the point of view of measurement-based quantum computing, as it relates to ZX, and also how this gives us polynomial time circuit extraction. Okay, so this is probably the most technical chapter in the bunch, but it's really developing a lot of the machinery that something like PYSIX uses under the hood. Chapter 10 is about controlled gates, multi-controlled gates, and classical oracles. Okay, I won't go into too much detail here. I just sort of put some keywords here. The main new ingredient we introduce here is these things called H boxes. So some people are probably familiar with the ZH calculus of me and Miriam from some years ago. These are a convenient way of representing things like multi-controlled gates. Like this CCZ gate looks like this constellation of phase gadgets, or it looks like a single H box. So in this chapter, we talk about multi-controlled gates, the ZH rules, classical reversible logic synthesis, and building arithmetic circuits. Okay, so this is really kind of building up from basic gates to slightly higher level things, using some tools like the logical structure of these gates and also the Fourier transform or graphical Fourier transform. Chapter 11, we add T gates. Okay, so you can tell, we've already been talking about universal circuits, but there's something that's quite special about T, and quite special about the Clifford hierarchy. And in this chapter, we start to dig into what that is and how we can take advantage of that structure. Okay, so the first thing we do is we talk about Clifford+T circuit synthesis. Okay, so we give a tutorial kind of introduction to the number theoretic circuit synthesis algorithm. So this is where you sort of iteratively transform unitaries over a certain field to the identity by applying T gates and S and H gates. Things like the least denominator exponent sort of apply here. So all of that machinery is developed. We also talk about spider nest identities. So that these are these things where I have these very complicated constellations of phase gadgets, which actually equal the identity, which are very closely related to triorthogonality. In fact, all of these spider nest identities are of the form of something that looks like this in the scalable notation, where I've got a triorthogonal matrix here. Or if this is some smaller phase angle, it might be some L orthogonal matrix, but this is a very standard, very regular pattern. We also talk about T-count optimization. So this is using things like Reed-Muller decoding or Todd-style 3-tensor factorization, which is all related to this triorthogonal type structure. And we also talk about a technique called catalysis, which is used for circuit synthesis here. So we develop this machinery of catalytic embeddings and show how you can use that to synthesize gates with small phase angles. Okay, so this is really a lot about circuit synthesis and optimization when we really have all of this special structure coming from the Clifford hierarchy. And the kind of final chapter of the book, the capstone chapter, is this QEC chapter. So this is about quantum error correction fault tolerance using ZX language. So QEC in general, or one way to think about it, is done by encoding some space of logical qubits into a bigger space of physical qubits. This thing, this encoding map, or maybe just this image, is a quantum error correcting code. And these codes are used to encode logical states, measure physical qubits, and do fault-tolerant computations. So the way that we talk to at least standard quantum error correction with ZX calculus is you can think about this encoder map as a ZX diagram itself. So we can take this thing, which has K inputs and N outputs, and just draw it as ideally a quite simple ZX diagram. And we can think about fault-tolerant quantum computing as pushing things through this encoder. Okay, so for instance, maybe I wanted to do a logical CCZ gate like this. Then if my encoder is nice, maybe I can push it through and I can get this, which is a transversal T gate, a T applied to all of these qubits. So for instance, the 832 color code has this property. And it has to do, again, with the triorthogonal structure, why you can do this. So for CSS codes, this encoder picture is especially nice because you can really express the logicals and the stabilizers of your code really directly into the diagram. Okay, so here's a few codes which might be familiar to some people. Here's the Steam code. You can see this kind of familiar cube appearing in here with the logical coming in there and the stabilizers sort of coming out there. Well, let's see. Yeah, these in this picture, the green nodes are the stabilizers. Yeah. This is an 832 color code, which again you can see it as a cube, but it's got some more inputs than the scene code. And here's a surface code, and you can kind of see this 2D surface structure appearing there. And in fact, we can even work with check matrices directly with CSS codes using the scalable notation. Okay, so if I give you the logicals and the stabilizers of a code as Boolean matrices, then I can draw its encoder and stabilizer in scalable notation this way. So you can use this representation for lots of stuff. So here, for instance, is a proof on one slide why CSS codes have a transversal CNOT gate. Okay, you can see that here's my physical transversal CNOT, and I've just pushed it through, and I've gotten a logical transversal CNOT. You can also use this to reason about transversal non-Clifford gates up the Clifford hierarchy. So when this thing describes a triorthogonal code, then we can take a transversal T-gate like this, and we can push it through, and we actually get a transversal T-dagger on the other side. You can use lattice surgery, or you can talk about lattice surgery in this notation. So here I've got two patches of surface code, and I've done measurements along the boundary between the two patches, and the thing that it gives me is a logical merge. Okay, so a lot of this kind of stuff is developed. And yeah, I guess I'll just mention a couple more things. But I'm almost done here. So fault tolerant syndrome extraction looks very nice in this picture. So here is a kind of a high level picture of a multi-qubit measurement, and here is Shor style syndrome extraction. And what's the difference in these things? Well, I've just unfused some spiders, right? So you can take advantage of this to think about a lot of things in the fault tolerance literature very easily. Magic state distillation. Here's a picture of magic state distillation. Of course, that's explained in the book. Okay, so that was a kind of a whirlwind tour of just about everything that's in there. I didn't mention some stuff, but I think I hit most of it. So yeah, get the book, I guess, and I hope you enjoy it. If you find a bug, please post an issue on the GitHub, so we keep an eye on those. And the thing is a kind of a living preprint at the moment, so we're sort of actively making fixes. And also, if you want to teach using this book, we have materials for you. So we've got problem sheets, model solutions, syllabuses, that kind of thing. So do get in touch. Okay, I think that's all I wanted to say. So thanks everyone, and happy to take questions.
All right. Thanks, Alex. So yeah, do we have questions? I see Sarah has raised her hand.
Yes. Hi, Alex. Thank you very much for the talk. I wonder, because a lot of people in China, they also want to learn ZX calculus, but they don't like kind of have the access to the translated version. Do you plan to have any translated version of this book? Like, for example, in other languages?
We don't have plans yet. So what happened with the last book? So we are publishing it with CUP. What happened with the Dodo book is that they actually did license the book for translation. So now there are Russian, Japanese, and Chinese versions of the books. Hopefully that happens with this book too. It kind of depends on the demand. But of course, there's going to be massive demand for this book, right? So in that case, I would expect a Chinese translation to come along, but it might be a few years yet before we have the sort of person power to do that.
And how do people let you know that they have demands for a translated version of this book?
Well, they can always get in touch with us and say, we would like that. We can definitely pass that on to the publisher. So
Okay, thanks.
Yeah, the fine people from Saclay.
Hello, can you hear me?
Yep.
Okay, so I will ask now the most important question, I think the one that everyone is thinking about. Like, is the Crow book the official name of this one, or?
Me and John have been calling it the Crow book for years already, so I guess you can refer to it this way.
I've been mostly referring to it as the ZX book, but yeah.
The ZX, but oh no, we're diverging.
Also, Constantino's asked in the chat, like, what's the name of the crow? The crow is called Coco.
Yeah, Coco. It is Coco the crow. Credits to Constantinos for for helping us come up with this name.
Yeah.
Contributed to science. Yes, that's right.
And Master Justy, it will be, for now, it's only online, right? It's not published in physical edition.
Yeah, that's right.
And you don't have any plan to put it in?
No, we do. So it's asymptotically approaching the point where we will send it to the publisher, which we've been saying is within a few weeks. We've been saying for at least 6 months now. But yeah, we're sending it to Cambridge University Press, and there will be a paper book. Once they have it, the turnaround time on that I think is about six months ish. So ideally within a year you'll have that on your bookshelf.
Okay, thank you.
See that Leah says that someone called it the Crow book to make it rhyme with Dodo book.
So yeah, I teach a course which is half based on this and half based on the Dodo, which I call the Crodo book or course.
I should add here that the book has been online for about a year now, and we've received quite a few sort of typos that people saw, and then we fixed it. But what we haven't really had is any sort of more high-level feedback on whether you think certain things are not as clear as they can be, or maybe the order of things is in the wrong order. So yeah, if you have opinions like that, we also very much like to hear them, because right now it's been our opinions on what works best, and then people have suggested small fixes, which we've mostly implemented. But yeah, especially if you're also using this for teaching and stuff, if you find certain things are confusing or weird, like, I don't know.
I have a question about encoders for non-CSS codes.
Mm-hmm.
How does that work? Is there some part of the theory that you would use for that? Is it just another normal form, et cetera, et cetera?
Yeah, so I think the story there is not fully complete yet, though there is definitely a story there. And I think it's really about using Clifford normal forms for these encoders. So you can get quite some mileage using either the GSLC normal form or the AP form as your encoder.
Yep.
And these both kind of have some pros and cons. The thing that you lose there is a direct connection with the stabilizer tableau. So unless you put your stabilizers into a particular form, then you can't just read them sort of straight off the diagram anymore. But that may not be such a big concern. And certain non-stabilizer codes do look quite nice in ZX as well. So for instance, the 513 code has that nice, very, very clear ring structure appearing and so on. But I think, yeah, I don't think we've hit version 1.0 of the non-stabilizer theory yet, but there are certainly some pretty functional beta versions out there.
Okay.
I saw that Konstantinos asked, has the QEC part become software yet? Or are students or engineers working on that? There are some QEC things implemented in physics, but there's no, I think, unified framework yet. I know various people, including Leah, have been talking about incorporating ZX QEC features into ZX Live and stuff. But yeah, I think there's interesting stuff to do there. People are working on it, but it's not like there's not a finished product. The talk of October 29th will cover some of this. Great, thanks, Jay. Who is Jay?
I see on October 27th there's a talk by Austin Fowler on TQEC, which is a different piece of software for doing topological quantum error correction, also using ZX.
Mhm.
So that's probably what's being referred to.
That's-
Unaffiliated with our work, by the way.
Yeah, and then there were various other comments about non-CSS codes. And yeah, okay. Any other questions?
I'm surprised there are no comments of like, why is my pet research topic X not part of the book? But maybe we have incorporated enough pet research topics.
Yeah.
But there is a kind of a tradition that each time there is a book out, it triggers research so that the book become as soon as possible obsolete. So
Yeah. Yeah, we've noticed that. Um,
I have a question about the software as well. So based upon a lot of the literature that you wrote together, you have this physics implementation. And do you plan to point certain section of the book to the software so people know like, oh, actually, these things have already been implemented?
So there was an original plan to create Jupyter notebooks for every chapter of the book. I still think that's an interesting thing to do. In terms of keeping this project on schedule, we've kind of separated that from the book itself. But that's, I still think that would be a nice way to structure a bunch of things and just release that as an open source contribution. And also maybe open that up so if other people wanted to contribute to that, I think that could be quite nice. Possibly other physics developers and so on. I was going to make a comment. So one thing that is missing from the book is completeness beyond Clifford's. So this stuff is pretty tough. I think we point to that literature, but we don't really go through those. We don't really go through those things in detail. So that's, if you're sort of a core ZX community person, that might be the one thing you think is kind of not in there.
Oh, how about machine learning stuff? Combining machine learning with the ZX calculus.
Yeah, I guess we don't really have that. I mean, maybe it's in there somewhat implicitly, like things about variational circuits. I mean, at least tools for working with variational circuits are in there because we spend a lot of time working with phase gadgets and Pauli exponentials and that sort of thing. But yeah, no sort of explicit QML things.
I mean, speaking of things that go outdated quickly, like talking about machine learning would instantly be outdated.
Yeah, I guess so.